the second speaker of today, Erik Panzer, about polylogarithms in deformation quantization.
Hello, good morning, good afternoon, wherever you are in the world. Thanks very much for running this conference in this very difficult time. I'm sure it's a nightmare as an organizer, but I'm very happy to see on the camera some people in the lecture room. Unfortunately, I couldn't be there, but I got my second dose now. So if it would have been a week later, I could have made it. But anyway, so regarding my talk, so I guess my talk is maybe a bit at the sides of the conference theme. So what I'm interested in is integrals and functions. And so I'm going to talk about particular aspects in quantization and deformation theory where certain integrals appear. And I want to say some things about what these integrals evaluate to in terms of numbers and special functions. So this is a joint work, a paper I've written with Peter Banks and Brent, where we looked at Kontsevich integrals in his universal quantization formula. And I'm sure this is preaching to the choir, but I'll just briefly review my point of view on all of this before I get to the details. So I guess my starting point is that quantization is some mysterious procedure to turn some classical description into some quantum mechanical analog, characterized by taking a commutative product and making it somehow non-commutative in the very first approximation. And the surprising thing about these quantization methods is that even though there's different, I mean, today we have many different methods to do deformation quantization, but somehow they're all, at some point, there's this ingredient where you have to solve a tower of equations, and somehow if you want to have an explicit solution, they all involve some kinds of integrals and some funny transcendental numbers like zeta values. And this is somehow the point where I got interested into this story. By the way, if you have any questions, since it's a 1-hour talk, feel free to ask in between, because if you're lost early on, then it's probably not much fun. Okay, so okay, the rough idea here is to start with a classical phase-based description with functions on a phase space and a time evolution equation given by a Hamiltonian and canonical brackets between position and conjugate momentum variables. In this picture, I'm just illustrating a particle described by a position and one momentum, a one-dimensional dynamical system. And the naive quantum mechanical analog is some wave function, which is a square integrable function. And there's a Schrödinger equation for the evolution of a state, or in the Heisenberg picture, you have a time evolution of an operator. So the hat always denotes some operator analog of the classical observable. And then we have canonical commutation relations that lead to the Heisenberg uncertainty principle. And this h bar, the degree, the size of this non-commutativity is really the measure of how quantum the system really is. And then going back to Dirac's prescription in canonical quantization, from this formulation, the idea is to mimic the effect of the commutator of the operators by the Poisson bracket. But it turns out that this is only possible to first order in h bar, and you have to have higher order corrections. But nevertheless, to leading order, there is this correspondence. And then when you look at the actual products, not just the commutators, then you're missing something on the phase space side, right? So if you have the product of two operators, use another operator, and if this is supposed to be a perfect equivalence, then you need a non-commutative product called the star product to reflect this non-commutative multiplication on the phase space description side on the left. And then the proposal in deformation quantization is to stay explicitly on the left-hand side and just talk about deformations of algebras. So I'm very quick on this, but I'm sure that everybody in this conference knows this much better than myself. So With this, then the algebraic description of what the deformation quantization does is the following problem. So we have given a Poisson bracket on, in the simplest case, just on Euclidean space. So it's an odd bilinear form. We have a Jacobi identity, and we have a Leibniz rule. And this is supposed to be the first order deformation of a product. So the deformation quantization asks whether we can complete this to an actual product. So I'm only talking about formal deformations. So I will treat h bar as a formal parameter and work with formal power series. So I will not discuss any convergence issues, although these are very interesting. But as a formal power series, you want this product to be associative, and it should be a deformation of the product. So to leading order in h bar, it should just be the commutative product. So when the h bar goes away, it becomes 0. We are back with the starting theory. So we have a one parameter family of products, you might want to say. And then for each order in h bar, there's some coefficient in this product that depends on the functions. It is supposed to be some differential operator. And the connection to the Poisson bracket is made by requiring that exactly this commutator of this product, which should correspond to the commutator in the quantum description, should exactly be given by I h bar times the Poisson bracket. So then the deformation quantization problem and this very classical setup is to find a solution, a set of operators that have this commutator here, but that also have the property that the resulting product is associative. And of course, this is a long story with different solutions in different cases. And I want to talk specifically about the solution given by Kontsevich, because this is one where the integrals come in that I want to talk about. So let me remind you of what Kontsevich's formula looked like. So this is a formula for a star product on RD for an arbitrary Poisson structure, Poisson bracket. And it's given in an explicit form. So you have a formula for the nth term, Bn f of g is the nth term in the h bar expansion of the star product. And essentially, it's given by a Feynman-like formula. So you have a sum over graphs, and then every graph contributes a number, wg, and this is the number I want to talk about. This is what I'm interested in. So this is some kind of Feynman integral of a two-dimensional field theory, Poisson sigma model. And then there's also another term that is now still called B, but indexed by the graph, which is a differential operator. And this is where the Poisson bracket goes. So this is a very important piece. But it's pretty easy to compute, actually. So if your goal is to compute these quantizations in some orders in h bar and see what they do, then these differential operator parts are actually not that problematic. And some of the more mysterious object is this wg. Also, this weight, this wg, does not actually depend on Poisson structure. So that's why this is called a universal formula, because these coefficients somehow they solve a universal problem. If you write out the associativity constraints in terms of these coefficients, they somehow decouple from these operators. So what are these graphs? So these graphs are called admissible graphs. But so essentially, what's important here for the star product is that you have two types of vertices. So there is black vertices that are drawn by black vertices. There's n of those. For every order in h bar, you get a new black vertex. And each of these black vertices has two edges going out. And there's two special vertices that I draw blue and always on the bottom. And they should also have an ordering. So there's one that's on the left and one that's on the right. And those don't have any outgoing edges. So this is a purely combinatorial characterization of a bunch of graphs. And here you see the only graph at n equal 1. And here you see the only graphs at n equal 2. And these are the only graphs because there's a set of rules here. So you're not allowed to have an edge that goes back to this vertex where it started. And you're also not allowed to have two parallel edges. And if you use these two side constraints, then you quickly check that these are all the graphs. And so then this formula shows you that if you want to compute the first term in h bar, you only have to compute a single integral and a single operator. And then at h bar to the squared, you have 4 different integrals and operators. So at every term, this is a finite, every order in h bar, this is a finite computation. And you can enumerate it like that. Okay, so what are these things actually? What is this operator? So I've chosen here an example. So there's a graph. This would contribute to h bar squared in the star product. So there's 2 black vertices. And then what you do is you replace each black vertex by a Poisson bracket. So we have 2 Poisson brackets here. And then the Poisson bracket of what? Well, you take your coordinates of your Euclidean space, x1 up to xt, you plug them into Poisson bracket. But then you also have to take derivatives. So every black vertex becomes a Poisson bracket. The blue vertices become the functions that you're acting on, f and g. And then every edge is a derivative. So this goes like this, right? So we have the top left vertex, xi, comma, xj is just a Poisson bracket. Then we have the other vertex, which is also a Poisson bracket, but it has an incoming edge. And that translates into a derivative with respect to the coordinate xj. So think of this edge coming out of the xj. And then we also have the f at the bottom left, which now has 2 incoming edges, so it gets 2 derivatives. And then finally, the g gets a single derivative. And ultimately, you're summing over all the indices. If I would have been proper, I would have had upper and lower indices, and it would be an Einstein kind of summation convention. So what you see here is just this operator. You see it's made out of the Poisson bracket and its derivative, and it's acting as a derivative on the functions f and g. So this simple rule is really all it is. So it's very easy to write down these operators. I mean, in principle, for large graphs. Of course, if you have an explicit Poisson structure, there's a lot of algebra to be done. But so these are these operators. And now the other ingredient, the topic of this talk, are these weight integrals, these coefficients. And that goes as follows. So what you do is you think of these points in the complex plane, or rather the upper half plane, actually. So what you do is that these left and right, the blue vertices, they're somehow special. They sit on the real line, and you can put the left one at the origin and the right one at 1. And then the remaining black vertices, they correspond to points in the upper half plane. So you have coordinates z1 up to zn in the upper half plane. And essentially, you don't know where they are. So in a kind of general quantum principle, if you don't know where they are, you should integrate over all possible positions. And that's what we're going to do. But then we also need an integrand, some Feynman rules. And that's given as follows. So for every edge in the graph, right, the edge goes from one of the vertices to another one. Now for every vertex, we have assigned positions. So it makes sense to talk about the difference of the position of 2 vertices. And then you can define these, what's called a propagator or harmonic propagator. It's a differential 1 form denoted d phi I to j. So it's associated to this edge from I to j. And it's the 1 form given by the derivative of the argument of this combination zi minus zj over z bar minus zj. So if you think about it, you can interpret this as a hyperbolic angle between infinity I and j. So you really should think of an angle. So it's divided by 2 pi in some sense to normalize it. And then because every internal vertex, each of these n vertices has 2 edges going out. So there's 2 n edges in total. So if you wedge together all of these differentials, you get a 2n form. But you also have a 2 n-dimensional space of degrees of freedom, right? The 2n real coordinates of the n points z1 up to zn. So the degree of the form and the dimension of the integration domain match. So you can consider this integral here. And indeed, that's the definition of these weights that Kontsevich proposed. So you can check that these actually make sense. So these integrals converge. And everything here in this argument formulation is real. So you get real numbers. And this is the kind of integrals that I want to look at. Just as a comment, maybe you have come across this, there is a variant of this. You can also use a slightly different propagator. You can replace these one forms by forms which are not real anymore. You can replace the argument by just the d log. So this may look nicer from some perspectives, but technically it turns out to be much more tricky, because with this it's not at all clear even that these integrals converge. So you have to do quite a lot of work, but luckily this has been figured out. So you can also use this set of weights, which is a different set of weights, and still everything you want will hold. So I also want to look at those. Okay. Now to give you a feeling how this goes, I'll do an example. And now this is a super simple example, and I'll probably do it in the most complicated way. But the point is that the way I'm going to do it will illustrate all the main ideas. I mean, most of the main ideas of our method. So bear with me. If you understand the following example, you have understood most of what I wanted to say. So let me try to walk you through this. So we have this graph. It's just a single black vertex and two edges going out. Right. So we're going to integrate only over the position of the black vertex. The blue vertices are fixed at 0 and 1. So we will get an integral over the upper half plane. That's it. Okay. Now, what are these edges? What are the integrands, right? So this is an edge from z to 0. So you get the argument of z, essentially. So you can write this as log of z over z bar. And the other edge is d of log of z minus 1 z bar minus 1. So if you look at it the way I've defined it, right, you're integrating a 2 form over the upper half plane, and it's a d log wedge d log. So it's obviously an exact form. So I've already written it that way. So I've just taken away the differential of the angle to the left. So now we have the differential of a 1 form that we integrate over the upper half plane. And of course, the idea is to use Stokes' theorem for this. So I just want to be very pedantic here to make sure you see what the subtleties are. So one of the problems is that this differential form alpha, it has singularities on the boundary, right? So there's problems when z is close to 0. There is a discontinuity when z is near 1, and also at infinity. So you cannot literally apply Stokes' theorem to the upper half plane. But what you can do is you do a kind of regularization trick, right? So I mentioned earlier that you know that the integral converges. So you can compute the integral by taking a limit over domains that exhaust the integration region. So you can look at these funny shapes where what I did is I cut out a little disk around 0 and 1, and I also cut out a little disk around infinity, which means I have this very large half circle here at infinity. And then if these radii of these small ones go to 0 and the radius of the outer one goes to infinity, you recover the original integral. But now when you're on this shape, and now your differential form is well defined, right? So you can apply Stokes' theorem to this shape, and indeed reduce the integral to the integral of a 1 form over this funny boundary. Now you have to look at the different pieces, the different components. So for example, when you're on the real line, so from these three real line stretches here, you actually don't get any contribution, because if z is equal to z bar, then this differential d log z minus 1 over z bar minus 1 is 0. So even if you get close to 0 where this log has a problem, the log is tempered by this vanishing of the 1 form. So you don't get any contribution from the real line. And similarly, you can check there's nothing from 1 or 0. So the way I have chosen this primitive alpha here, it turns out that you only get a contribution actually from this arc at infinity. And now something funny happens when you get close to infinity, right? Then z minus 1 over z bar minus 1 is the same as z over z bar. So your 1 form is log times d log, or a half d of log squared. So now you use Stokes again, essentially, right? So now you have this 1 form, which is itself a differential of a function, and then you just evaluate at the endpoints. And if you check what happens, right, z goes to I pi, then z over z bar gives you 2I pi, and this goes away, and you just get the half as a prefactor. I mean, this is all elementary complex calculus here, but I think it nicely illustrates what's going on. So this is probably the most complicated way to compute this this 1/2, that is this first Kontsevich rate. But what does it tell us in this case, right? So we have computed the first term in Kontsevich's formula. There's only this one graph. The weight is a half. If you remember how the differential operator works, right? We just have a single Poisson bracket and then a single derivative on f and g. And that's just another way to write down a Poisson bracket in coordinates. So what we've checked is that the first term in the Poisson, in the star product of Kontsevich's formula is a half IH bar times the Poisson bracket. And that looks pretty reasonable, because that means that the commutator will then be exactly IH bar times the Poisson bracket as it has to be. Okay. But now the question is how to generalize this kind of procedure to arbitrary of these weight integrals. Okay. Just waiting for a sec if there are questions. I can't see the chat, by the way, when I'm presenting like this, so you just have to shout and tell me if there's anything. Okay, so let me just continue here. So a bit more generally, let's do the following. So far we have looked at graphs with n black vertices and 2 blue vertices. So more generally, consider graph with n vertices and m blue vertices. And then we also introduce a more general space that we want to integrate over. So you should think of these as configuration spaces of marked disks. So imagine a disk. I mean, I have a tendency to write it as the upper half plane. You may consider it as the actual disk, whatever you prefer. So we have n points, n marked points that live in the interior of the disk. And we have m points, the blue points, which sit on the boundary of the disk. So far we had only 2 points on the boundary, and I fixed them to 0 and 1. And so we're only left with the upper half plane times n. Now, more generally, you have these n points that 1 up to zn. In the upper half plane, you have the m points q1 up to qm on the real line. They are ordered. And then you're modding out by a 2-dimensional symmetry group. So the symmetries you have of the disks are in the upper half plane model, they are the translations in the horizontal direction. And you have scalings, real scalings of everything. Right, so when you think again of m equal 2, you can use these two symmetries to always move q1 to 0 and then scale so that q2 is at 1. And then you're in the representation I gave you earlier. So we have these configuration spaces of disks with markings in the interior and on the boundary. Then the simple dimension calculation shows the dimension of these spaces 2n plus m minus the two-dimensional symmetry group. Then in particular, we have 2 points. So if you have only one internal point and no marking on the boundary, or if you have no marking internally and 2 markings on the boundary, in both of these cases, you have a point. There's only one equivalence class. But in all other cases, you will get higher dimensional spaces. Now, when we have a graph now with n black vertices and m blue vertices, then what you do is, as before, for every black vertex, you associate the coordinates zn as z1 up to zn. For the blue ones, you now use the coordinates q1 up to qm. So you can still make sense of these forms, these propagator forms for each edge, and you can wedge them together to get a differential form on this configuration space. So you can consider those integrals. But it turns out there's a more subtle thing that you can do, which is instead of integrating over everything, you're only integrating over some of the coordinates. So notice there are these forgetful maps. So if you have a disk with n plus r marked internal points and m plus s marked points on the boundary, then you can forget some of these internal markings. And you can forget some of the boundary markings. And then you just get a disk with fewer markings. So you have these forgetful maps. And then you can integrate just over the fibers of those. So imagine like you're keeping a bunch of these z's and q's fixed, and you're integrating only over the positions of a couple selected ones. So one way to notate this is like this. So you write an integral over this forgetful map, which means you get a function on CNM, which you obtain by taking a graph with n plus r black vertices and m plus s blue vertices, and integrating out the last r internal point and the last s boundary point, say. And as an integrand, you always take this wedge product of these propagator forms. And in this way, again, now you define also a function on a form on CNM. But what this means is you don't always have to integrate out everything, right? So you can still get functions, not just numbers. I will come back to this later. So I hope this is somewhat clear. Now, what are applications of this in deformation quantization? I mean, the ones that I've seen explicitly are as follows. So I've already mentioned the star product, right, where we have the special case where the graphs have 2 blue vertices only, right? So we only see these types of integrals in the star product. Actually, it's even more restrictive, right? Because the graphs here were of a special type where you only have 2 outgoing edges per black vertex. So this is a very restricted subset. But then you probably know that there's a deeper theorem in this work, the formality morphism, that gives an L-infinity quasi-isomorphism between the Pauli vector fields on RD and the Pauli differential operators. And then you want to write down what does it mean to have an L-infinity morphism? But explicitly, it means that for every n, you have a map that takes n Pauli vectors, gamma 1 up to gamma n, and spits out for you some Pauli differential operators. And this is a direct generalization of the star product formula. So what you do is now you sum over graphs with several black and blue vertices, and you're integrating over these CNMs, these weights. So this is why even in the standard deformation quantization, you already see the cases with more than 2 blue vertices. Said in a different way, the star product really should be seen as a consequence for Maurer-Cartan element of this formality morphism. All right, so you really see all of these graphs with arbitrary n and m showing up here. And now what about these fiberwise integrals? There are different places where these kind of objects show up. So, for example, when you know about this familiarity morphism, right? So you get a quasi-isomorphism of these differential graded d-algebras, then you might notice there's also a Gerstenhaber bracket on the polyvector fields and the polydifferential operators. And you might wonder, how does the quantization formula of Kontsevich respect that, or not respect that? And it turns out that actually you can lift these L infinity morphisms to homotopy Gerstenhaber morphisms. So, and this means you're introducing new components to your morphism, which tell you how the Gerstenhaber bracket is related in higher order correction terms. And one way to write this down explicitly was done by Wilwacher. And this uses exactly these types of integrals that I mentioned, where you're actually talking about graphs that have n black, n plus r black, and m plus s blue vertices, and you're integrating out only over those extra ones. And then you get differential forms on these configuration spaces. And it turns out that you can make this into a map of operad. So actually, when you go to a compactified version of these configuration spaces, then these differential forms you get from integrating over these fibers, they actually restrict nicely to the boundary strata and so on. They respect all the structure. So this is one application where these things show up. If you haven't seen this, maybe you have seen something similar known under the formality of little disks. I mean, there's also different approaches, but one method uses a similar construction, which in some sense you should think of as a special case of the previous one, where somehow you don't have any blue vertices, you only have black vertices, and things get a little bit simpler. So in this universe, the configuration spaces only have a single index, but still you have very similar integrals and similar graphs. And then one way to prove the formality of little disks is again by considering integrals over these fibers of such forgetful maps. Okay. So from now on, I will really focus on these integrals as an object in themselves. So I'm not sure I'll make much reference again later on to applications in quantization. So this is just to motivate why this might be interesting for this conference. Okay, so what are these integrals? That's the question we wanted to investigate. And there has been a huge effort to understand these integrals in many special cases. So for low orders in H bar and for many special types of graphs that are very important, there have been many insights and calculations. And I'm not showing you all of them, I'm only showing you the simplest here, in particular the most deceptive ones. So these are the first two orders in the star product, right? The graphs I've shown earlier. Just to remind you that you can have arbitrary numbers of blues. I also drew this graph here at the end, which has 3 blue vertices. And in this case, all these weights are not too difficult to compute, and you get these simple numbers here. But it was noticed pretty early on that the story is much more complicated. So Felder and Wilwacher have pointed out that there are graphs where these integrals involve zeta values. So let's look at this one here on the left. It's not exactly the one from the Felder-Wilwacher paper, but it has the same feature. So when you express this in terms of known objects, then you have a little rational number and a rational multiple of zeta 3 squared over pi to the 6. So zeta 3 here is really the Riemann zeta value. It's Aporis constant, the sum over the inverse cubes. And I will recall later that conjecturally this ratio is not a rational number. So there's no way conjecturally to simplify this any further. So somehow rational numbers are not enough. And to show you even more extremely what happens, I've cooked up this weird little zigzaggy example here. Where you have a rational number, then you have two zeta values, zeta 3 and zeta 5. But conjecturally, this number cannot be written in terms of Riemann zeta values alone. There is something here at the end, which I denote zeta 3, 5. And what is that? Well, that's a double sum that I've written here. So it's a nested sum over cubes and fifth powers of the summation variables. So it's in some sense, a generalization of the sum for the Riemann zeta function to a double sum with a nested summation range. And again, conjecturally, you cannot get rid of such double sums if you want to write down this kind of number here. So this is just to illustrate, so you've seen some examples, and then the result is pretty intuitive from here on. So what you do is you define what's called multiple zeta values. So just as a reminder, there's the transcendence conjecture. So all of these zeta values, zeta 3, zeta 5, zeta 7, and so on, they're assumed to be algebraically independent, and they're also assumed to be algebraically independent from pi. So under this, if this is all true, then zeta 3 squared over pi to the 6 should not be a rational number. To the best of my knowledge, this is still just a conjecture to this day. But this is the reasoning why you don't expect these numbers to be rational. Now, as I hinted already, it is not enough to look at just zeta values. You have to introduce what's called a multiple zeta value. So let me do the full-blown generalization. So I showed you the single and the double sums. Now you do just the default sum. So you can have now S1 up to SD arguments in your zeta function. And it's a default nested sum, K1 less than KD, of the inverse powers of the case with exponents given by the arguments of the zeta function. So these are called multiple zeta values, and they're a huge domain of research in themselves. Maybe you have seen them in the coefficients of the Knitznik-Samologikov associator, but they show up in different places. Just one notion that I will use is the sum of all of these indices. That's called the weight. I can get back to this in a second. If you don't know these zeta values, what you should keep in mind is that there's a lot of relations among those. So for example, zeta 2 is famously just pi squared over 6. And similarly, every even zeta value can express in terms of the power of pi and a rational number. So for example, zeta of 4 is pi to the 4 over 90, and so on. But there's also relations among more complicated multiple zeta values. For example, zeta 1, 2. So that's a double sum you could write down. Turns out you can rewrite this and show that it's the same as just zeta 3 again. So what that means is if you're on weight 3, so you want all the arguments to add to 3, then by going to these multiple zeta values, actually you don't get anything new. You only get zeta values again. Similar in weight 4. So if you're in weight 4, you can write down the following multiple zeta values: 1, 1, 2, 2, 2, 1, 3, and 4. But as you see here, you can actually prove that they are all the same up to a rational prefactor. So again, at weight 4, you don't gain anything by going to the multiple world, so to say. But as I showed you earlier, actually there is new numbers coming in eventually at higher weight. And now the theorem is that if you take a graph with n black and m blue vertices, then the weight is in Zn plus m minus 2. So the weight is n plus m minus 2 at most, where by this Zw I denote the space you get by linear combinations of all the multiple zeta values divided by the corresponding powers of I pi. So maybe you have noticed earlier that we always divide by a certain power of pi, I pi. That's because the pi shows up in the propagators in exactly this way. So here I've shown you a little table where you see the generators of these spaces Zw. And notice there's an I here in the denominator. So this may seem weird, but as I mentioned earlier, there is also what's called a logarithmic propagator, which is not real. And in that case, you do get complex values for the weights and the integrals. So this is why the imaginary parts can also be interesting. But if you're in the original world with the real harmonic propagator, then you're only interested in the real part and the real numbers of this form. And basically, I've explained some of these features to you already, right? So we know that in way 2, zeta 2 is just a power of pi. So if we divide it by pi squared, we just get a rational number again. Similarly, in weight 4, we only get rational numbers. In weight 3, we would have zeta 3 divided by I pi cubed, but that's an imaginary number. So if you have a real integral, it cannot be anything like that. And a similar thing happens in 5. So it turns out that weight 6 is the first time that you can write down multiple zeta value with this normalization that is real, that is not rational, at least conjecturally not rational. And it's exactly the zeta 3 squared over pi to the 6. And if you do the analysis further, then you find that at weight 8, you have exactly 2 generators. So this is the first time where you get a multiple zeta value that you cannot possibly, conjecturally, you cannot rewrite in terms of just ordinary Riemann zeta values, and so on. So conjecturally, we have an understanding of these type of generators in low weights. And then by these reasons that I mentioned earlier, because of these gaps here, this implies that the first 5 orders in H bar always have rational coefficients. But I've shown you examples at 6-plex vertices where you have this ratio. Okay. Now just an example, so that all of this is available as software. So it does 2 things. On one hand, it expands. You can enter a Poisson structure and it gets expanded into the different graphs, and it works out the operators. But the second part is also that you can actually compute these integrals, and they're tabulated up to h bar to the 6, but you can compute higher ones if you need them. And here's an example of the so-called log canonical bracket. So that's on R2, and it's a quadratic Poisson structure of this type. So the Poisson bracket of x comma y is x times y. And this is just to illustrate that these transcendentals don't disappear, right? You could argue maybe they cancel out in the sum over everything with some signs or so, but this is not the case. So if you compute the star product, the Kontsevich star product with a harmonic propagator in this example, you get the following expression up to order h bar to the 6. So you get some not so meaningful rational terms in the beginning, and then you see some multiple of this conjecturally transcendental number, theta 3 squared over pi to the 6, actually showing up. So it doesn't cancel between the graphs. But what is interesting to note is that if you actually compute the star product the other way around, you get a similar looking thing. And then you can wonder what is actually the ratio of x star y over y star x, because this is the quantity that classifies the automorphism class of the algebra. And then when you go there, you get this cancellation that actually you just get the power series expansion of the exponential function. And I think there's some understanding for quadratic Poisson structures why this could happen. But at least on the level of the star product itself, you still see the transcendentals. Okay, so far I've only talked about numbers. I think I want to say at least a few words about functions. So what about these fiber integrals? I'm just giving you some examples here. So what does this mean? That the first example, we have 3 black vertices, and I'm just integrating over the third, but I'm keeping the first and the second marking. So what I will get is a differential form that depends on Z1 and Z2. Now in this case, because I have a 2 form, I have 2 edges, and they're integrated over a 2-dimensional space of positions for the third point, what I will get is actually a function, i.e. a 0 form on C2, 0. And you can compute it, turns out to be that thing. Z1 minus Z2 bar over Z2 minus Z1 bar, the logarithm. And indeed, you can convince yourself that this is a well-defined function. So wherever you are, however these 2 points move around, this logarithm never crosses the branch cut. It's a single-valued real analytic function. So this makes sense. But you can also have situations like the one below, where now you have 3 edges, so you're integrating a 3 form. So after the integral, what you will end up getting is a 1 form. And in this case, it's a simple product with the earlier function, but just to remind you that in general, these things will be differential forms with coefficients that are real analytic functions of the coordinates, okay? And finally, just one more example to show you that it's not everything logarithms here. So what I'm doing here is I have 4 black vertices and I'm integrating out 2 of those. Again, you have 4 edges of 4 form and you're integrating over 2 vertices now. So again, it's exactly the dimension of the fiber. So you're just getting a function and not a differential form. And it turns out with a bit of massaging, you can write it in that form. So you have some constant. You have the function we saw earlier squared. And then you have something else which you cannot write in terms of logarithms, no matter how hard you try. You need to introduce a new function. And this is the dilogarithm function. So the polylogarithm functions, they start with li1, which is essentially just logarithm of 1 minus z. And it is useful to remember that you can write this as an integral of dt over 1 minus t. So this is the first polylogarithm. And then all the higher polylogarithms, well, on one hand, you can write them as a power series expansion, z to the k over k to the s. So in particular, notice that it means that the value of lis at z equals 1 is exactly the Riemann zeta value at s. But you also see from this power series expansion that you can write it as an integral. Right? So if you integrate dz over z, you can decrease the power of k in the denominator step by step. So you can write the higher polylogarithms as integrals over of dt over t times the lower polylogarithms. Okay, so now you know what the dilogarithm is. You can think of it as a sum over z to the k over k squared, or you can think of it as an integral of the logarithm times dt over t, or you can think of it as a double integral of dt over 1 minus t, and then you integrate again dt over t. And it turns out that this point of view, of this iterated integral point of view, is very useful and a practical tool to compute with these functions and to understand the properties. So I hope it is clear what these functions are, at least roughly. They're well-studied special functions with many nice properties and algorithms to manipulate them. Now, let me just summarize the results very briefly here. So there's two ingredients. So one is, where's actually the integrand from, right? Our initial integrand, the omega g, was built out of the wedge product of these propagator forms. So you have d logs, and what do you find? I mean, you find zi's minus zj's, you find zi's minus zj bars, and then you find also Zi is minus the q's, or Z bar is minus the q's. So you take all of these rational forms, and the algebra they generate, that's what I call A. So this is, A stands for the Arnold forms. It's like the subalgebra in the algebra of forms that's coming from these Arnold, generated by these Arnold forms. That's where the integrand lives. And then we need these special functions. So how do we get these? The first trick is the geometric procedure. So we have the disk, and you glue the disk along its boundary to its conjugate. So what you get is a curve, which is the complex plane minus the positions of the points z's and their complex conjugates and the q's. And now on this curve, you can talk about iterated integrals. And I'll show them on the next slide, but it's basically the construction of the polylogarithm. So you get holomorphic functions in these variables z and z bar and q by doing iterated integrals. Again, I'll show them on the next slide. So these are called LW of sigma. So they're indexed by some positions of these singularities that you're integrating over iteratedly. So this VNM is an algebra of hyperlogarithms in these, which are holomorphic in these coordinates z, z bar, and q, viewed as individual variables. And then you ask yourself, well, which of these functions are actually well-defined, i.e. single-valued, when you think of z bar as the complex conjugate of z? So this defines a subspace, a subalgebra of these functions, which has no monodromy along the real part of the space that corresponds to the configuration space of disks. And this is the space of polylogarithms that shows up as coefficients. So then the theorem is that if you're doing such a fiber integral, what you get is an Arnold form with coefficients that are these single-valued combinations of multiple polylogarithms. Okay, so maybe I'll just review quickly in a simpler case how this goes, and come back to the calculation at the very beginning, but in a simpler setup. So maybe for now, let's forget about the boundary of this funny shape in the upper half plane. Let's just do the following. So suppose you want to compute this integral. Yeah, this looks similar to what we have. It's a product of Arnold forms, dz bar over z bar, and then we have dz over z minus 1 and dz over z minus p. Okay. But now let's suppose you integrate over the complex plane. This is a procedure that's to me was introduced by Oliver Schnetz, and is a simpler version, which is now often referred to as single-valued integration, and has applications in string theory. But how does it go? So we do the same kind of procedure. So the first step is to find a primitive, right? So we can just write this as d log of z bar times the rest. And we want to apply Stokes. Now there is two problems here. Right? The first thing is, again, we have the singularity, so we have to cut out little holes and take a limit that we discussed earlier. But now we have a new problem, because this function log z bar is actually not well defined, because it has monodromy, right? Because in our integration domain, z can now go around 0. Previously, this couldn't happen because we had the real line as a boundary. But now z can go around 0, so log of z bar is not a well-defined function, so it doesn't make any sense to apply Stokes' theorem. Now the magic is that you can always make it single-valued. So instead of log of z bar, you could have also chosen log of z bar plus log of z. And notice that this doesn't change the fact that this is still a primitive, because if you take the total derivative of this part that you added, that's 0, because that's a totally holomorphic one form. So you maybe start with the bad choice of a primitive, but then you can always make it single valued. There's a recursive procedure that does this. What you do is you compute the monodromies, and then there's a way to cancel the monodromies step by step. So there is a filtration somehow and the monodromy goes down in the filtration. So there's a finite algorithm that gets rid of all the monodromies. So now we made it single valued, which we needed because the integration domain was not simply connected. And then we do the same procedure as previously. We truncate, we apply Stokes, and we integrate over these little circles and the large circle at infinity. And in this case, if you work it out, you just get log of absolute value p squared in this particular example. So I just want to recap for you what these steps in the calculation are. And then to sum up, so what do? We introduce a space of functions, which are the hyperlogarithm functions. So they are given by iterated integrals. So they're described by a string of letters, which are chosen from this alphabet Z, I, Z bar, I, and Qj. So all the punctures on your glued curve. Then you can always integrate dt over t minus one of these punctures times the previous function. So if you define these functions, then in particular they include the polylogarithms, but they include many more functions. And they're called multiple polylogarithms or hyperlogarithms. And the multiple zeta values, they arise as special values when you only allow sigma to be 0 or 1 and you evaluate at 1. Remember, I mentioned earlier that the Riemann zeta values come up as the special values of the polylogarithms. And the same generalizes to this multiple situation. And then what we do is to construct these functions. So initially we start with such holomorphic hyperlogarithms, and then what we're doing is we're adding complex conjugates, and then we use complex conjugation to cancel the monodromy. And what you get up in the end is functions that are given as bilinear combinations of holomorphic and anti-holomorphic polylogarithms. And these are called single-valued polylogarithms, introduced by Francis Brown. And yeah, I should sum up, but with this procedure, you can then apply Stokes. You can use these single-valued coefficient polylogarithms to find primitives and apply Stokes. And in the end, what you do is you reduce this integral over the complex plane. In some, this is a very rough intuitive formula here, into a line integral. You only do a single integral and 2 pi I from the residues around the loops. And this is my very last slide. So also, by the way, this story here, this is how you compute these integrals in the formality of little disks. Yeah, so you have this factorization in holomorphic and anti-holomorphic terms, and you can compute the integrals in this way. And now, if you want to do this more general story for the disk integrals, what happens is you have these extra pieces, Zi is equal to Zj bar coming from the real line, which is the boundary of the disk. So this makes things a little bit more complicated, so you don't have this perfect factorization anymore, but still you can work with these hyperlogarithms, and still you can show that the space is still big enough to cancel the monodromies. The Stokes theorem gets a little bit more complicated because, as in the very beginning I showed you, there's this real boundary. And another annoyance also comes from these corners. So in this picture that I drew, you have the real line and you have these little circles you cut out. There's corners. So actually you're doing Stokes on a manifold with corners. And this causes some problems where you need to define some regularizations. But in the end, you're done with that as well. Okay, maybe I stop here. This is a good point. Thanks for your attention, and I'm happy to answer any questions.
Thank you very much for your talk. Are there any questions?
Yeah, thanks again. Very beautiful talk. I have just one question. So there is, you mentioned this Gerstenhaber G infinity formality.
Yeah.
Thomas Willwacher. And but of course it was proven in another version earlier by Dmitry Tamarkin.
Yeah.
Used instead of he had to use was for associators instead.
Yeah.
You have, say, two versions with Kontsevich integrals and the other one with the Drinfeld associators. Is there? I'm a very stupid question. Is there to compute the correspondence? So can you express Kontsevich integrals in terms of Drinfeld associators, or vice versa? Is there?
Yeah, very, very good question. Thank you. So indeed, so I've exclusively focused here on the story where everything is written in terms of configuration space integrals. You're absolutely right. There's very different approaches, especially the Tamarkin's approach. And so on one level, Willwacher and collaborators have explained a connection between the two approaches. So there's a theorem that the Tamarkin approach, if you choose a certain associator, which is the arXiv associator, that it is homotopic to Kontsevich's formula, Kontsevich's formality morphism. But from this point of talk, basically, what you could wonder is maybe there's an explicit way to take an individual Kontsevich weight and rewrite this in terms of coefficients of an associator. And actually, I think this is exactly what's happening. You see, it's maybe a bit hidden and it's very indirect. But how does this? Yeah. So what are we doing? So these polylogarithms that I'm using as building blocks, these hyperlogarithms, those are the coefficients of the Kniznik-Zamolodchikov connection. And what I'm doing is I'm taking coefficients of the Kniznik-Zamolodchikov connection, and I'm combining them in a way to make up functions which are single valued on these configuration spaces, and I use these functions to define differential forms in order to compute my integrals. At the very end of the day, when I've integrated everything, so suppose you're not looking at fiberwise integrals, you really integrate out everything. Then at the very end of the day, you all the way boil down again to just multiple zeta values, which are coefficients of the Drinfeld associator. So, and on top of that, everything here is using like these transformations of integrals, equivalences of period Stokes theorem. So I think indeed this is an algorithm that explicitly, in some very convoluted form, rewrites a Kontsevich weight integral in terms of combinations of an associator. But it's very, very convoluted. I mean, I wouldn't be able to write it down in a neat little equation.
But there's still the algebraic frame. I mean, Drinfeld associators are, of course, the conversation of linear algebras or even quasi-linear algebra. So there is an algebraic frame which makes the identity more.
Sorry, I can hardly hear you. Can you speak a little bit louder?
No, I'm just I can understand that the Drinfeld associator is made out of polylogarithm, etc. So if you this I understand, and then but there's also this algebraic frame of these Drinfeld associators, and using quasi-Hopf algebras, etc. And so, but is there also a relation in this direction, as far as you understand?
I mean, by frame you mean like quantum groups or the whole theory of
Hopf algebra. So I mean, Drinfeld associator first served as quantization of Lie algebras, and it was the dequantization part which Tamarkin had been forced to use. Yeah.
Yeah.
So this came in like this, and so one might wonder, you are aiming at associativity somewhere, and there is also a monodromy which is also associative. I mean, I'm talking rubbish, but
no, I know what you mean, and I see so some of the bottom line of all of this, right? Whatever you do, you cannot really get rid of an associator. Somehow it always sits inside. Either you use it as extra ingredient in Tamarkin's approach, or you do Kontsevich's, which doesn't at first look like an associator, but we know already the work of Dolgushev that the stable formality morphisms form a torsor under GRT, and there is actually a map from formality morphisms to associators. And in some sense, you could view what I said as yet another instance of this connection, that every integral is expressible in terms of coefficients of an associator. But I cannot say anything more, less unsatisfying, I'm afraid.
Are there any more questions?
Hello.
Hello.
Hello. No, thank you very much for this great talk, very inspiring. So I have two questions. The first question is that I have seen, I mean, you showed all these formulas, and I wonder if there is a relation with modular form theory, because I've seen this kind of formulas in this one.
What kind of formulas are you referring to, like for the integrals or for weights, or
the log thing that appears everywhere? You know, differential of logs, and then funny functions inside.
Well, okay, there's a lot of D-logarithms here. That's just how the weights are defined, right? And there's polylogarithms. I mean, there is one connection to modular forms that I'm aware of, which comes to the theory of multiple zeta values, but I'm not sure if that's what you're referring to. So there's this thing that if you want to classify multiple zeta values by their depth, then you have funny relations coming from cusp forms for SL2Z. But from my point of view, this comes from a different, so some of the connection between modular and multi-zeta, at least from my understanding, only goes through the elliptic world somehow. If you're elliptic, you can degenerate to a nodal sphere and get zeta values, but also you have modular forms floating around. And there is work by Francis Brown that connects modular forms to polylogarithms to this bridge. But I'm not sure I understand what you mean by or what a modular form connection would be outside of that.
I don't understand. This is.
It's a great question. I mean, one thing I'm wondering about actually is the entire approach that I explained. I mean, what it really relies upon in the end is using these path integrals, these iterated integrals on a surface, and then combining them to get an integration theory, a good model for the de Rham cohomology of the surface. And I'm wondering the same about higher genus surface. So actually, the whole story you can also do it on an elliptic curve, and that also has applications in string theory. So you can do these single-valued integrals on an elliptic curve. You get single-valued multiple polylogs, and those have direct connections to modular forms. So in that universe, you can write things either as elliptic polylogs or as iterated integrals, like higher generalizations of Eichler integrals of Eisenstein series and things like that.
That's what I'm talking about. Yeah, that's the type of formulas that they.
Yeah. So I fully agree. In that universe, if you go to the elliptic curves, then you have a beautiful interplay between the modular and these iterated integrals, and that's a very, very active area of research at the moment.
Yes. Yeah. Okay. Thank you.
Thanks.
I have another question. I forgot. That's a very. You talked about the log canonical bracket, right? So you disappear.
I think we lost connection to Erik.
Yeah, I don't see him.
You're still there. Friendly picture that we have.